now look at two examples for our functions graphically, algebraically, numerically, and verbally notes. This first example is simply showing the four ways to represent a function. So here is our situation. You pour a cup of coffee but forget to drink it. The coffee cools rapidly at first and then less rapidly, finally approaching room temperature. So this situation is talking about two quantities that vary. It's talking about time, right, as the coffee sits there, and it's talking about the temperature of the coffee. This is a verbal representation of temperature as a function of time, because there is only one temperature at any given time. If you think about our definition of a function, it follows that if temperature is a function of time, then for every time there is one and only one temperature, which would be true. Let's look at these. So that's one representation. Let's look at two more. The temperature of the coffee is measured at 5-minute intervals, and we have this data. So in this table, we have a set of points. We can see that at 0 minutes, when the coffee is poured, it is 90 degrees Celsius. Then after 15 minutes, the temperature of the coffee is dropped to 22.5 degrees Celsius. This is a numerical representation of the function. Next to this, I have a graphical, right? I have a graph. It is a graphical representation of the function. Okay. Remember that a graph is just made up of a set of points. So if we look at this graph, we have a point right here, and that point is telling us that at 0 minutes, when the coffee is poured, it is at 90 degrees Celsius. This is our temperature intercept. Right? Our temperature is our y variable. We have a dotted line here. This is not a part of our graph. Our graph is this curve, but it is an asymptote, which is at room temperature and showing that the temperature of that coffee decreases, right, getting closer and closer to room temperature. The final representation we're going to look at is this. We have here an equation, and this equation is an algebraic representation of our function, and it is a mathematical model for the temperature of the cooling coffee. So let's look at this. Could we use this mathematical model to find the temperature, right? Our temperature is our y, of the coffee after 8 minutes. 8 minutes is a time, that is our x. Well, we can. If we come in here and we leave y unknown, that's what we're trying to find, and we replace our x with our given time, which is 8 minutes, and we evaluate that, right? And remember, you would do exponents first, then multiplication, then addition, right? You can use your calculator as an aid. You would get 31.744 degrees Celsius. Let's take a look at another model we have of this. The equation is one model, the graph is another. So we could also use our graph to estimate that temperature, right? We're finding the temperature after 8 minutes. So if we go to this point on the time axis, that would be at 8 minutes, and we follow that vertically until we reach our graph, take that point on the graph and follow it horizontally, right? It intersects the temperature axis at about 30 degrees Celsius, just slightly above that. So the graph is a model. It gives us an estimate for that temperature. The algebraic equation actually gives us a more exact estimate, 31.744. Well, let's reverse this. Could we use our equation, right, that mathematical model, to find the time, again our time is our x, when the temperature of the coffee reaches 50 degrees Celsius, that's our y. So if we replace y in our equation with 50, and we write our equation, leaving x as our variable, to find that time, we would need to solve this equation. Well, what does it take to get x by itself when it's in an exponent? Well, hopefully, right, you're saying it would require logarithms, which is true, right? But you're probably also groaning about having to use logarithms. And I want you to tell you, for right now, no worries. We will come back midway through the year and review logarithms, and you will become quite adept at being able to do that. For right now, we won't solve this algebraically, but we can go back to our graph and we can get an estimate from our graphical model. So looking again at our graph, we want to find the time when the temperature is 50 degrees. So we go to 50 degrees on our temperature axis, and we follow a line horizontally until we intersect our graph, and then take that down vertically till we intersect our time axis, and see that that happens at about 4 minutes. Okay, so not an exact, right, but a pretty good estimate of that time. So those are our 4 representations of a function. We started with verbal, then numerical with points, then graphical, and then algebraic. We will use all 4 of those representations throughout the year. Let's go on and look at our second example. This time we're going to draw a graph from the situation. We have a tennis ball that is thrown over a house. So we've got a house. And if the tennis ball is being thrown over a house, there must be a person. And that person has a nice green tennis ball. And let's say that person is you, and you're going to take that tennis ball and you're going to hurl that over the house. And it flies over that house and it lands in an empty swimming pool. So we've got a swimming pool here that the tennis ball lands in. Now, this is not a graph. This is just an illustration of what's going on. Our job in this problem is to draw and label a graph showing the height of the tennis ball as a function of time. So if we're going to draw a graph of a function that involves 2 variables, which functions do, we need 2 axes. Our independent variable here is time, and our dependent variable this time is height. So our independent variable, time. Our dependent variable, height. Let's go on and let's answer a couple questions, and then we will come back to finish this graph. What would a reasonable domain be for this function? Remember that domain refers to reasonable values for our independent variable, which is time. So if we take that tennis ball and we throw it, right, when time is 0, we are just releasing that tennis ball, right? And if it flies over that house and it lands in the swimming pool, let's think, 1001, 1002, 1003, 1004, 1005. Guessing, but maybe we have times that go from 0 through 5, and that would be in seconds. I'm going to give that domain in what we call interval notation, where these brackets tell me that time can be 0, can be 5, and the comma says it can be anything in between. If we want to identify the range of our function, that range refers to our dependent variable, which is height. So we want to think about our lowest height. Well, if we go back to this drawing, the lowest height isn't here, right? That's where the ball takes off, but the ball actually reaches a lower height when it comes and it lands in this swimming pool. So let's say this is a 10-foot deep swimming pool, which means our lowest height would be -10, and the highest height would be, right, the peak of that path. And let's say if it flies over a one-story house, maybe it reaches 25 feet. So we're measuring this in feet, and in interval notation, this would be our range. So if we come back and think about our graph, we have times that are going from 0 to 1, 2, 3, 4, and 5. And we have heights that are reaching as high as 25 feet, so if I do this by tens, and as low as -10, so if I come down. So a reasonable graph, this is not perfect, right, but based on our guesses, would be where the ball starts. So let's see, here, right, maybe that ball starts at 5 feet. And that ball rises up to 25 feet and then comes back down, and then after 5 seconds lands in the bottom of the pool. Does this graph look like any graphs we're familiar with? Right? Well, hopefully you're saying, yeah, that looks like a parabola. And a parabola is the graph of what type of a function? Right? Well, it is a graph of a quadratic function. Could we now use the graph to determine the height of the tennis ball at a given time? So if we come in here, could we say find the height of the tennis ball after 3 seconds? Well, if we go to 3, follow the line up to the graph, and then a horizontal line over, we could estimate that maybe after 18 seconds, the ball is at a height of 3 feet. Okay? Could we use the graph to determine the time at which the tennis ball is at a given height? And so could we run that backwards? Could we say, determine at what time the ball reaches a height of 10 feet? Well, for that, we would take a horizontal line till we reach the graph, and then vertically, and say maybe after, I don't know, 0.4 seconds, it reaches a height of 10 feet. But if we take that horizontal line and continue it, we see we intersect that graph again at maybe 3.8 seconds. So for this one height, 10 feet, we actually have 2 different times. The time on the way up, the ball reaches that height, and then again the time on the way down. So, why is time not a function of height? Okay, let's use our definition. If time is a function of height, then for every height there is one and only one time. So, time is not a function of height because for this height, there were actually 2 times. The remainder of these notes you'll finish on your own as you work through the problems that are associated